Okay, just as a quick overview of the balance calculator, this right here is calculating or actually demonstrating the calculated results of the vector forces at the crankshaft. This is top dead center and it's going around here. This is 90 degrees. This is bottom dead center, 270 degrees. This black right here is the average, so you can visually see how it's varying from the average. All those calculations having been done mostly down here. And so the vertical to horizontal ratio is demonstrated right here. And let me show you what I mean. So you've got the lopsided circular graph of the crank rotation and the forces. It's like actually, let me show you. So right here at TDC, you've got a vertical force of that amount. And then 30, 60, 90. Right here, you've got that. It's not completely horizontal. Look at that. It's somewhat downward. That's at 90 degrees. Then you've got bottom dead center. And then you've got 270. 6 right here. So those are the vector forces. And what I found works is taking this section of the vertical close to TDC and this section of the lower portion, which includes a little bit more of this horizontal effect out here, and compare the two. That's the vertical, that's the horizontal. And so you can call that also top dead center, bottom dead center. 1.0 is the ratio. That's at 6100 on my engine. At 5100, you can see that the horizontal is more than the vertical, which creates an imbalance. So that's off by 3%. And then at 7300, it's off by 5%. So we got the vertical and horizontal computed here, and then when you figure in the actual average forces involved, this is the graph that you come up with, which is like more like what you feel, okay? Which on my bike it's 4% off for most of the RPM up to the high RPM. So I'm going to show you what happens when you reduce the hole size. One of these holes here close to the conrod pin, if you reduce the hole size, see it becomes more vertical? Because these holes on this side, not on this side, these holes on this side counteract the piston assembly weight. And if you don't have enough holes to counteract that, then the vertical difference becomes more. And the same thing if I make the holes too big, then I've reduced the vertical a lot and it's got a lot of horizontal component there. So right here is the maximum engine RPM, the very top that your engine will rev out to. The top end compression ratio is figured in. That little dip right there, that's due to the compression. Okay, there's a little calculator for that. Down here, this section right here. And every cell that has a red corner on it, you should hover your pointer over it so you can read what the hidden comment is to be fully informed. Figuring out the holes in the connecting rods reduces the weight of that section, the small end or the large end. And then you've got rectangular slots. They also do the same thing. So this section is also necessary to fill in because it is utilized in this cell and this cell. I'm not 100% sure about the counterbalance shaft, the extra balance shaft that some big engines have, but here's the input for it, and you can read about it, the grams and the distance from the center of the shaft. So after entering everything, you just click this right here, and it will recalculate for both of these graphs. And you can see visually, or you can just look right here, and it will tell you what RPM, at what RPM those graphs cross the 1.0 mark. And in this case, it's 6,600, which is right here. Which is good, because if my bike revved all the way to 7,400, then that would only be 2% off. But generally speaking, I like that 1.0 to be at this, somewhere along this section right here. Ideally, it will be beyond what this section is. For instance, let's say my bike revs out to 6,300, and I calculate. You can see how this is dipping a little bit farther down than what I like. This is like 6% down. So you have to consider the whole thing. You know, are you going to be mostly at the high revs? You're trail riding and street riding. You're using the whole range. When that 1.0 is to the left of the very end of the graph, you can see that this right here doesn't dip down as far. This is a 4% difference right here. Mostly just as long as you don't have more than 2% at the very top RPM. So this is the number of holes per set. Like, these are the same size, and they're located at the same position of the crank as far as degrees from this center line of the connecting rod pin, which is right there. So this is a set. This crank wheel has 2 holes. The other crank wheel has 2 holes. So that's a 4-hole set. This right here is just 1 hole on this wheel, 1 hole on the other wheel. So that's a 2-hole set. And then the number of the hole fillers right here. And these are the main inputs you can choose. If you want to use something else, then you just enter a number 6 right here, and you enter in the density of the metal that you used, if you filled a hole with a different metal, that is. It's a pretty complex program. It's not really complex to you. There's just a lot of measurements to be made, all these measurements here. And you've got to know your compression ratio. If after you've done everything, hopefully you entered everything in correctly, and this is showing a 1.0 at a different RPM than where you feel it's happening at, the 1.0 representing the high RPM at which you can start to feel it starting to vibrate more. So if that's not harmonizing with what you feel, you can make corrections right here. You want it to be 10% lower, you do that, or you want it to be 10% higher, you do that. So this is the correction factor. But usually it's pretty right on if you did all the measurements right. So I guess that's all for the basics of the program. If you have any questions, let me know.